In Derby, England, something extraordinary happens every 36 hours. A new Rolls-Royce jet engine comes to life. It begins not with sparks or flames, but with thousands of parts, titanium sheets, precision fasteners, and hollow fan blades, moving through a synchronized flow of people and machines. Inside the vast warehouse, teams clock miles daily, collecting over 30,000 components per engine. Those massive fan blades, each weighs nearly nothing, yet carries the thrust of 13 double-decker buses. The fan alone pushes 1.2 tons of air every second, making up 75% of the engine's thrust. Bonded under high pressure and formed with classified processes, they're then put through explosive tests and ultrasonic inspections before final assembly begins. Modules converge on the production line, and within 36 hours, a complete engine, sleek, tested, and certified, is ready to power the skies. It's not just about building power. It's about building trust, one flawless rotation at a time. From glowing steel to forged perfection, this is how a 900 kilograms coupling is born through traditional Japanese free forging. Each piece starts as a raw cylinder, its surface still coated with mill scale from prior processing. The process begins with S45C steel, a medium carbon material favored for strength and machinability. Heated until red hot, the billet is transported to the forging station. The temperature must exceed 1,200 degrees Celsius before the steel is malleable enough to shape. Unlike die forging, free forging requires no molds, just skill, muscle memory, and a blacksmith's intuition. With a team of skilled workers, every strike of the power hammer reshapes the metal. The rhythm of the hammer is controlled manually, in sync with the metal's response. At this stage, both sound and color guide the operator more than sensors or screens. First, the surface scale is removed, allowing clean contact with each blow. Then the shaping begins. The hammer compresses the billet, gradually forming the cylindrical body. Forging direction alternates in stages to ensure balanced internal grain flow. Height and symmetry are monitored continuously, adjusted by eye and with calipers. No automated systems here. When the color fades from bright yellow to orange, the window for effective forging begins to close. One slight tilt, one uneven strike, and the entire shape could drift off spec. Workers coordinate verbally, adjusting timing, and angle strike by strike. It's not just brute force. Timing, temperature, and angle matter. Too cold and the steel cracks. Too hot and the structure weakens. As the forging nears final dimensions, blows are lighter, more precise. At 900 kilograms, this coupling isn't just big, it's precise. Workers rotate it between strikes to ensure even pressure distribution. Sparks fly, the forge roars. But the result is quiet beauty in steel. Final touches may involve small corrections with handheld hammers or trimming tools. Hey, why free forging? It's ideal for low volume or prototype parts, where flexibility and responsiveness matter more than mass production. It's also more cost-effective than cutting from solid bar, wasting less material, and preserving grain flow. The integrity of the grain structure helps improve both strength and fatigue resistance. Despite its importance, free forging is becoming rare. It takes years to train a master. Fewer workshops remain, but some, like this one, continue to pass the torch. Watching this process isn't just about metal. It's about legacy, craftsmanship, and the enduring art of shaping steel by hand. Under the glow of a magnetic field, steel heats, spins, and hardens. Welcome to the world of spin induction heat treating. Used for massive sprockets and traction wheels, this process hardens only the surface, right where wear happens most. The part spins beneath an induction coil, generating intense heat through electrical current. In seconds, it reaches transformation temperature, then quenches instantly with a controlled spray. Surface hardness rises dramatically while the core stays tough and ductile. Every setting, spin rate, coil position, temperature, is programmed and recorded, ensuring consistency across all parts. Operators even test cross-sections to verify hardness, depth, and pattern. It's fast, targeted, and ideal for rugged machinery. Need to treat a one-off prototype? No problem, this setup handles it. From giant rings to thick wheels, this process ensures durability where it matters most. Under massive pressure, flat steel transforms into a perfect curve, hydraulic forming at its finest. It starts with a flat steel plate, precisely cut to the desired diameter. The blank is placed onto a forming die inside the hydraulic press. From above, a matching punch descends, applying slow, even force. This isn't brute smashing. It's carefully controlled pressure that allows the metal to stretch and flow into a smooth, curved profile. Throughout the cycle, hydraulic pressure can exceed hundreds of tons. Operators monitor the forming depth and flow to ensure perfect symmetry. No folds, cracks, or thinning. The process delivers uniform thickness and stress distribution across the surface, critical for components like pressure vessels and tanks. Once formed, each dish end is trimmed and prepared for edge machining or welding. No reheating or hammering required, just clean, cold precision through hydraulics. Hydraulic forming is ideal for thick plates and large diameters. It's quieter, safer, and far more consistent than traditional hammer forging. Watching the steel curve effortlessly under pressure is oddly satisfying. Form and function, working in harmony. Watch raw steel evolve into complex geometry. No pause, no guesswork. The Okuma LB3000 EXMYW, a multi-axis CNC turning center, shows what happens when dual spindles, live tooling, and synchronized motion come together. We begin with a solid steel bar held between the main spindle and sub-spindle. The machine selects its tools one by one, starting with a roughing tool loaded with a triangular carbide insert, cutting at 200 meters per minute with a 1 millimeter depth of cut. Then it switches to the same insert, now running faster, 300 meters per minute, with a shallower cut for smoother finishing. Next comes a finishing tool, equipped with a diamond-shaped insert, great for fine detail. It takes lighter passes, again at high speed, demonstrating the machine's ability to move seamlessly from roughing to finishing without stopping or reclamping. Complex shapes come next. A form cutter carves deep profiles at 600 RPM, removing 8 millimeters of material in a single pass. Then a grooving tool steps in, cutting precise channels at a feed rate of 1.5 millimeters/rev. From profiles to grooves, the level of control is razor sharp. A contouring pass follows, using a polycrystalline insert to maintain surface integrity at high cutting speeds. The Y-axis comes into play for offset milling, making angled cuts impossible on simpler lathes. Drilling is fast and steady, driven by a synchronized turret that aligns each motion perfectly. Chamfers and radii are created in a single move, using multi-function cutters to reduce tool changes. Live tooling adds even more flexibility, allowing end milling, tapping, or slotting operations right on the turning center. Tool wear compensation is monitored in real time, adjusting offsets automatically to maintain precision. And once one part finishes, the sub-spindle takes over, flipping it for backside machining. No human touch required. The CNC program handles it all: tool changes, spindle sync, torque monitoring, executing every command with tight tolerances. Driven tools on the turret enable milling while the part rotates, boosting efficiency even further. You can almost hear the rhythm. Cut, retract, swap, repeat, thanks to the twin spindle layout. While one side machines, the other is already prepping the next part. That means no downtime, just continuous, synchronized production. Feed rates and speeds can even be adjusted mid-cycle, putting the operator in full control. It begins with crates, cables, and colossal castings. Inside IDRA's Italian facility, a third-generation Gigapress takes shape piece by massive piece. Capable of casting aluminum parts as large as a full car chassis, this Gigapress is among the most powerful manufacturing machines in the world. These massive die-casting machines are built to shape the future of automotive manufacturing. Assembly starts with structural steel frames, delivered in sections due to their enormous size. Overhead cranes guide each part into place with surgical precision. Columns, crossheads, and tie bars are aligned and fastened, forming the mechanical backbone. Next, high-tonnage hydraulic cylinders are mounted. These will later apply clamping forces exceeding 6,000 tons to mold molten aluminum into a single cast part. Every connection is torqued and retorqued to ensure long-term stability under intense cycles. The injection unit comes next, assembled separately and craned into position. Operators install electrical systems, cooling lines, and sensors, each integrated with the machine's computerized control. It's like watching a skyscraper fused with robotics. The final phase is calibration. Tolerances are checked, systems pressurized, and dry run cycles performed. Once testing is complete, the Gigapress is ready to ship, its destination likely a major EV factory. Building something this size isn't just impressive, it's necessary for modern production. And seeing it assembled step by step, that's a rare look behind the scenes of a giant. Where others stop, this machine starts. The SDMC 12,000 tackles oversized workpieces with zero hesitation. With a fixed table and a double-column design, this beast handles massive components with ease. The X-axis travel spans from 5,000 to an incredible 30,000 millimeters. Built from solid cast iron, the base, columns, and bridge offer unmatched rigidity. Dual ball screws and preloaded rack and pinion systems ensure accuracy across long travels. The spindle delivers high torque through a gearbox head, ready for demanding cuts. Tool changes take just 7 seconds, and dual chip conveyors keep the workspace clean. This isn't just machining, it's controlled power on a monumental scale. It all starts with steel bars, but inside Rain Engine Valves Plant 2 in Medchal, those bars are transformed into high-performance engine valves through a precisely coordinated series of operations. The journey begins at the raw material store, where cut bars are prepared for pre-machining. Next comes upsetting, a forming process that reshapes the bar's end, followed by forging using high-tonnage presses. Once forged, the parts undergo solutionizing, a heat treatment that improves durability and uniformity. Even at this early stage, precise timing and temperature control are crucial. Minor variations can compromise final strength. Next is a critical step, joining different steel grades. Friction welding and button welding are used to fuse dissimilar materials, followed by deflashing to clean the joint. The result? Strong, seamless components. Machining operations follow, turning the head diameter, facing, and copy-turning established geometry. Seat grinding and centerless grinding refine surfaces. Then, induction hardening is applied twice, once to the seat and again to the stem end for enhanced wear resistance. Chrome plating adds corrosion protection. Plasma-transferred arc welding reinforces the seat area for extreme durability. Operators follow digital process sheets and use calibrated tools to keep every valve within microns of its spec. The rhythm of production is unrelenting. Each step flows into the next with minimal handling and maximum control. Every valve is tested. Leak testing, multi-gauging, and eddy current inspections catch the smallest flaws. Magnetic particle inspection identifies hidden cracks. In the QA lab, profile projectors, contour recorders, and roundness testers ensure dimensional integrity. Finishing steps include laser marking for traceability, oiling to prevent rust, and multi-stage packing that prepares the valves for global shipment. What looks like a simple part hides a highly engineered story of durability and control. Heat. Massive loads. Massive loads. Zero margin for error. At ThyssenKrupp CSA's steel mill in Brazil, raw iron travels through a fully integrated logistics system built for safety, scale, and precision. It starts at the blast furnace, where molten metal is tapped into torpedo ladles. The multi-mover M700, with a staggering payload of 700 tons, transports the glowing cargo to the pig casting machine. Remote control ensures each move is deliberate, smooth, and safe. No human proximity needed. To move slag, the Slag Taurus P120 steps in. With overload protection and a protected support system, it dumps waste with controlled force. Multi-mover Y550 handles red-hot deliveries to the deposit area, navigating tight industrial paths with excellent maneuverability. This isn't just about heat. It's about enduring it with zero compromise. Witness how a 114mm stainless steel tube is shaped with stunning precision. The CH120 CNC gets it done. Operating in fully automated CNC mode, all three axes move in harmony to shape thick tubing effortlessly. Springback is compensated automatically, and anti-collision tech ensures safety throughout. From loading to forming, every step is synchronized, making this machine ideal for tough industrial jobs. Aluminum sheets enter the factory floor, but what leaves is refined, non-stick cookware ready for your kitchen. Molten metal is cast into sheets. This is where cookware begins. Once cooled, these flat sheets are cut and pressed into pan shapes, using heavy-duty forming machines. Edges are trimmed, the sides are lathed, and the bottom is milled flat to ensure even heating. A non-stick coating is sprayed on and baked at high temperatures. Each surface is inspected for even coverage and adhesion. Then the cookware packed, ready to turn everyday meals into effortless moments. Molten copper flows like fire. This is where copper tube manufacturing begins. At temperatures exceeding 1083 degrees Celsius, the liquid metal pours into molds, forming solid billets roughly 10 meters long. These billets, weighing about 450 kilograms, are water-cooled and reheated to around 850 degrees Celsius. Then comes the most impressive step. Under 3,150 tons of hydraulic pressure, they're extruded through a die and central mandrel, transforming solid cylinders into long, hollow tube preforms. Right after extrusion, rapid water cooling prevents oxidation. Each billet is precisely analyzed for chemical composition before casting. Even slight variations could affect final tube performance. Afterward, the extruded tubes are pickled to remove surface oxides, leaving a clean finish for further processing. Next, cold drawing refines both the diameter and wall thickness. The copper is pulled at speeds reaching 1,000 meters per minute, producing tubes over 120 meters long. This speed is astounding and essential for efficiency. Multiple passes may be needed to reach exact tolerances. Between stages, inline testing ensures consistency in wall thickness and concentricity. The length of tube drawn depends on its final use: short straight lengths for plumbing, long coils for HVAC. Technicians monitor every pass in real time, adjusting parameters based on live data. Even the slightest surface defect is flagged and removed before final processing. To reach optimal flexibility, coils are annealed, heated to approximately 650 degrees Celsius. After annealing, each tube is straightened or coiled, cut to length, and wrapped in plastic. Dimensional accuracy and surface quality are checked to ensure compliance with NF and EN 1057 standards, giving users confidence in every meter. Copper tubing production is a fascinating journey of metallurgy, pressure, and control, delivering a material used every day but rarely understood. This clamp once machine complete method eliminates extra handling and errors. The process starts with a solid cylindrical workpiece held by the main spindle and tailstock. An initial rough turning pass removes bulk material, preparing for finer milling. Next, the B-axis tool head rotates into position, and the mill spindle engages to cut precise gear profiles in one clamping. Using standard tools through WFL's flank cycles, flanks hob, spline, and large module, the machine can handle everything from small pinions to large involute spur gears. It adjusts feed, speed, and depth dynamically, making profile accuracy consistent across every tooth. The SiNumeric control and crash guard software monitor cutting forces and prevent collisions in real time. For jobs that demand extreme precision, thermal compensation helps maintain accuracy even during long machining cycles. Even asymmetric gear geometries are no challenge. Adaptive cycles adjust cutter paths automatically. The machine's rigidity ensures no chatter, even on deep or steep profile cuts. Operators can simulate full jobs offline, and pre-verify cutter engagement using digital twins. This minimizes downtime and improves first-pass yield. After gear cutting, the system performs in-process measuring with a probe, checking tooth geometry and concentricity on the spot. If slight deviations occur, live compensation tweaks cutter paths before batch completion. This feedback loop ensures gears leave the machine ready for use. No extra measurement steps needed. Heat-treated or hardened gears can be finished in the same cycle using soft or hard machining options. Tools swap automatically for grinding or hobbing heads, allowing everything from coarse roughing to final finishing. Parts up to 520 millimeters in diameter and several meters in length are all doable on the same platform. The result? Less rework, tighter specs, and more reliable gear performance under load. It's a future-forward approach that keeps pace with rising quality demands and shrinking production windows. Gearing solutions wrapped into a single machine. That's the WFL philosophy. It's about minimizing setups, maximizing precision, and boosting throughput, all with fewer machines and less floor space. Whether it's worm gears, helical shafts, or giant spur gears, the MILLTURN tackles them in one go. For gear makers, that translates to tighter tolerances, shorter lead times, and confident consistency.